10 says that standing waves on a 1 meter long string that is fixed at both ends are seen at successive frequencies of 36 Hz and 48 Hz. Part A asks, what are the fundamental frequency and the wave speed? And Part B asks to draw the standing wave pattern when the string is oscillating at 48 Hz. So first things first, we're going to list our knowns and unknowns. Let's start with our unknowns with the fundamental frequency. We'll call that F1. And the velocity we don't know as well. The knowns that we have the length of the string being 1 meter long. We have these two successive frequencies of 38 Hz and 48 Hz. These aren't necessarily F2 or F3, but they are successive frequencies. We'll just label them F2 and F3 for now. And F2 will be 36 Hz and F3 will be 48 Hz. So the difference in the successive frequencies will give you the fundamental frequency. We'll label that equation F1 equals F of m plus 1 minus F of m. So F of m plus 1 is going to be F3 and F of m is going to be F2. And that'll give you F1 equals 48 Hz minus 36 Hz. And this will give you a fundamental frequency of 12 Hz. Now that we have this, we can use this fundamental frequency to give us the velocity. We can use the equation of F1 equals mv over 2L. M will be 1, and the v is what we're trying to look for. So we can simplify this to be v by multiplying 2L to both sides. We can get v equals F1 times 2L. Plugging in the values that we have for F1 and L, we get V is equal to 12 Hertz times 2, and then L is 1 meter. This will give us a velocity of 24 meters per second. So we found our fundamental frequency and we found our velocity. Next up is to draw the standing wave pattern when it's oscillating at 48 Hz. So to do that, we need to understand that the successive frequencies are factors of 12, as you can see here. So we're going to know that F1 is equal to 12 Hertz. And then F2 would be equal to 24 Hertz. F3 is going to be 36 Hertz. And F4 is going to be equal to 48 Hertz. So I told you at the beginning that these don't necessarily mean that these are the second successive frequencies, just that they are successive. So now that we know that at m equals 1, it's going to be 12 Hertz, m equals 2 is equal to 24 Hertz, m equals 3 is 36 Hertz, and m equals 4 is 48 Hertz. These m's are going to correspond with the number of antinodes as well. So there's going to be 4 antinodes on this wave. So now we're going to need to find the wavelength lambda. In order to find the wavelength lambda, we're going to use the equation Fm equals v over lambda m. We're going to use the fourth frequency, which is 48 Hertz, because it's asking us to draw the string oscillating at 48 Hertz. So we're going to do F4 is equal to V over lambda 4. We can simplify this to lambda 4 is equal to V over F4, plugging in the values we have of 24 meters per second over 48 Hertz will give us 0.5 meters for the value of lambda at the frequency. So now that we know the wavelength, we know that the nodes occur at every lambda over 2. This is going to give us the nodes occurring every 0.25 meters. Now we have all the parts we need to draw the wave pattern. So we'll just go ahead and label it like this. We know that the L value L is equal to 1 meter. We know that the wavelength is 0.5 meters. And so this is going to be about 0.25, 0.5, 0.75, and then 1 meter. It's going to look something like that. As you can see here, there's 4 antinodes corresponding to the 4 modes. And the full length of the string is 1 meter, and the wavelength is 0.5 meters. So this is at 48 hertz, and basically what we found in the beginning is the fundamental frequency. We used this equation here to get the wave speed, and then in order to draw the wave pattern, we sketched the standing wave using the found values of lambda.